Now that we know how mathematical induction works, we're going to use it to prove some more interesting things about graphs. And these are proofs that will come back many times in the course situations where we're going to use induction to prove things about graphs. The first thing we're going to do is we're going to give an estimate of the number of edges in a graph. So the theorem says as follows. Assume you have a simple graph that has n vertices, and you know that the graph has k connected components. Then the claim is that the number of edges is at least n minus k, and at most this number, 1/2 times n minus k times n minus k plus 1. So how do we prove this? This is quite a complex statement. The proof will be slightly long, so bear with me. Before we get into the proof, let's look at the special case where k equals 1. In the special case, our graph has just one component, so it is connected. It's a connected simple graph. So the statement then says that a connected simple graph has at least n minus 1 edges and at most 1/2 times n minus 1 times n edges. So this numbers you probably recognize. This number is the number of edges in the complete graph on n vertices. So it makes sense. A simple graph cannot have more edges than the complete graph on this many vertices. This is the number of edges in a path, or more generally in a tree. So for example, if n is equal to 4, we have this kind of graph, or say n equals to 5 to make it more interesting, something that looks like this. So it has 4 edges, and none of them are in a cycle. And such graphs are called trees, and they will be the topic that we will study in the next chapter. But now let's go back to this general theorem. So we want to prove two things about the number of edges that we call m. We want to prove that m is at least n minus k. This we will do by induction. Later we will also prove that m is at most this complicated number. For that we will use a different reasoning. But let's start with the blue statement. We want to prove that the number of edges is at least the number of vertices minus the number of components. So this is the number of vertices, and this is the number of components. So for example, this graph has n equals 5 and k equals 2 because it has 2 components. So let's use induction on the number of edges. So we fix the number of vertices and we look at the number of edges. The base step is in a graph where we have no edges. So we want to prove that a graph with n vertices and no edges has at most, for that graph, the number of edges satisfies this thing. Well, if the graph has n vertices and no edges, it's the null graph. So it's going to be just the n vertices totally disconnected from each other. They will sit in n components. The number of components will be the same as the number of vertices. Well, in that case, what do we have? In that case, n minus k is exactly 0, and m is 0. So we need to prove that 0 is greater than or equal to 0, which is true. So the base case, it is done. Now let's go to the induction step. You have your graph with m edges, n vertices, k components. Remove an edge. What are you going to have? Well, the remaining graph still has n vertices because you didn't remove any vertex. It has m minus 1 edges because you removed one edge. If the edge you removed did not disconnect the graph, then you will still have k components. The edge you removed might have split the graph up into 2 components. So you might have then, it might have split one component up into 2 components. So the graph now, instead of k components, has k plus 1 components. So these are the 2 possible cases. Let's look at each of them. By the induction hypothesis, we can assume that the graph that now remains satisfies the thing we want to prove because it has fewer edges. So we reduced our statement about m edges to the statement about m minus 1 edges. So for this graph, the induction hypothesis holds, meaning that m minus 1, the number of edges, is greater than or equal to n minus the number of components. If we have k components, then this is n minus k. But if already m minus 1 is greater than or equal to n minus k, by moving the 1 to the other side, we conclude that m is greater than or equal to n minus k plus 1, which certainly is greater than or equal to n minus k. So in this case, by assuming the induction hypothesis, so this is the hypothesis, remember we are assuming that the statement is true for all cases with smaller number of edges, we can say something about the number m. If the graph we obtained has k plus 1 components, now the hypothesis looks like this. Remember, the hypothesis is our statement, but for one edge less. So the statement says, as it says here in the title, that the number of edges should be vertices minus components, at least. Now we have n vertices minus k plus 1 components. The ones cancel, and we conclude that m is greater than n minus, or equal to n minus k. So by induction, we conclude that in general, the number of edges is greater than or equal to n minus k. This was a long one, and there are lots of variables. Go back and go through the proof and make sure that you understand it. Noting that the only thing that we play with is the number of edges. The number of vertices is fixed. Now let's do a different argument to prove that the number of edges is no bigger than this complicated thing. So we have our graph with k components. We want to prove that the number of edges doesn't exceed this upper limit. So, of course, the number of edges will be the greatest if each of our components is complete, if each of our components has as many edges as possible. So if we can prove that such a graph doesn't exceed our number of edges here, then we're good. So let's try to prove that. So we want to prove that a graph consisting of k components, each of which is a complete graph, such a graph has no more than this number of edges. Now I claim the following, that if you have a graph with k complete components, the way to achieve the greatest possible number of edges is not to have one component, say, on 3 vertices and one of 4 vertices. No, what you want is to have one giant component with all edges sitting in this component, and all other components are just isolated vertices with no edges. So since you want the number of components to be k, and you want k minus 1 isolated vertices, the remaining vertices will have to sit in one complete graph with n minus k minus 1 vertices. Okay? Let's prove this claim. So assume you have your graph, one component has h vertices, the other has j vertices, and h is somewhat bigger than j. So I replace my I take from the poor and give to the rich. I replace my big component with an even bigger component. Instead of h, now it has h plus 1 vertices. And I take that vertex away from the smaller poor component that now has j minus 1 vertices. If I do this, this will increase the number of edges. Why is that? Because the number of edges I had from the beginning, so this is the number of edges in the complete graph with h vertices. This is with j vertices. Here now I have h plus 1 instead of h. And here I have j minus 1 So there is a typo here. This plus needs to be a minus because my new graph now has j minus 1 vertices. And now I claim that the number to the left is smaller than or equal to the number to the right. It is an exercise for you to develop the parentheses if you have too much time and check that this is actually the case. But the point is that making this large component larger and the small component smaller will increase the number of edges of the graph. So to have a maximal number of edges, what I should do is have this one huge component with all the edges and all other components isolated vertices. This proves the claim. And now, once I have proved the claim, the theorem follows, because such a graph, this monster graph, where I have one component which is the complete graph on n minus k minus 1 vertices and the rest isolated vertices, well, since the isolated vertices don't have edges, the number of edges of such a graph is the number of edges in the complete graph on this many vertices. And this is precisely this number, because the complete graph, remember, has 1/2 times number of vertices times number of vertices minus 1. And this is exactly what we get here in terms of number of edges. So to summarize, the largest possible number of edges in a graph on k components is obtained if k minus 1 of these components are just isolated vertices and one component is huge, is complete on the remaining vertices, and that component will have this desired number of edges, and this proves our theorem. As a consequence of that big theorem, we have a criterion for connectedness. If ever you see a simple graph and you know that it has more than this number, n minus 1 times n minus 2 divided by 2 edges, then it has to be connected. Why is that? Well, the theorem tells you that if it has k components, that means that it will have no more than n minus k times n minus k plus 1 divided by 2 edges. And if k is more than 1, so if the graph is not connected, then this number is smaller than or equal to n minus 1 times n minus 2 divided by 2. And therefore, if the graph has more than this number of edges, it must be connected. Logically, this makes sense. If you take a graph, it's a simple graph, so you can't put all the edges you want as loops on one vertex. You have to sort of distribute them in a reasonable way. Well, if the graph has too many edges, at some point you cannot keep components apart. You're going to connect the graph more and more. So that's the philosophy behind this corollary.